Thank you for joining us for today's webinar. Going to give everybody just another few seconds to join here, and then we'll get started. All right. Good morning, good afternoon, or good evening, whichever is applicable to you, and thank you for joining us for today's webinar titled Privilege Escalation in ZOS Systems, APF, and More. Most users and programs on ZOS run unprivileged, but exceptions matter. Vendor tools, system functions, and specialized applications often require APF authorization, execution in a system key, or access to restricted storage. In this webinar, we'll cover the role of APF authorization in supervisor state execution, how macros, system calls, and instructions manage privilege elevation, best practices for securing and managing privileged functions, insights on ZOS security scanning and compliance, and more. This presentation is sponsored by Precisely Software. Precisely is a recognized global leader in enterprise data integrity products for mainframe, mid-range, and distributed systems. For more information on Precisely, please visit precisely.com. Our speaker today is Principal Technology Architect Steve Pryor. Steve has more than 30 years' experience in storage management, design, and support, and speaks frequently at industry events. Prior to joining Precisely, Steve made important contributions at several mainframe software vendors, designing and implementing major products and components. At the end of the presentation, we will have a short Q&A session. Attendee microphones are muted for the presentation, but you may ask a question or request webinar assistance at any time during the webinar through the Q&A interface. After the webinar, all registrants will receive a link to the slide deck and recording. Thanks again for joining us today. Take it away, Steve.
Thanks, Ray. Good afternoon, everyone. My name's Steve Pryor. I'm with DTS and now with Precisely, and so you'll notice this month's webinar slides are somewhat more purple than they have been in the past. But we are going to continue this series of webinars because they've been very popular and particularly, we think, useful for not only people that are new to the ZOS platform, but also people that have been around in ZOS as long as I have, because every time I do one of these webinars, I discover things that I didn't know, and sometimes there are things that are surprising, and I'm wondering why I didn't know that. And so I'd like to we like to put these into webinars as sort of a public service. And so today, what I want to talk about is what in most of the universe is called privilege escalation. They have various terms depending on whether you're on a Unix system or some other system, but in ZOS terms, we're primarily talking about APF authorization, or we're talking about authorization in general. And so before we can talk about authorization, when you talk about authorization, when you talk about privilege escalation in general, you're talking about being able to do something that only the system should do. And so with, as the saying goes, with great power comes great responsibility. And so ZOS has, starting back as far back as OS 360 and 370, back in the early 1970s, IBM put out a system integrity statement that said, this is the sort of integrity you should be able to expect from an IBM system. You should be able to expect that no program that isn't supposed to do so will be able to circumvent system controls or disable things or alter things that they're not supposed to. And so there is a system integrity statement that has been updated for every mainframe release since 1973. And it's really very simple. It says that in terms of mainframes, or in terms of ZOS, system integrity means that no unauthorized program, no program that is not empowered to do so, can either bypass storage protection because main storage, virtual storage, has protection mechanisms associated with it, and so you shouldn't be able to touch something or alter something that you don't have access to. You should not be able to access a protected resource, and we're primarily talking about RACF, but it might be top secret or whatever your SAF compatible security system is. You shouldn't be able to access resources and bypass resource access control. And you shouldn't be able to obtain control in some sort of heightened state, authorized state, if you're executing instructions. Those instructions should not allow you to do any of those other things. And so IBM, this is sort of the cornerstone of IBM systems, and I don't know that any other manufacturer produces such a statement. Now, this is not to say it's the ZOS systems are always perfectly adhere to the system integrity statement, but IBM is committed to saying, well, if we don't, we'll fix it. And so let's talk about authorization in general and what's authorization. It's pretty straightforward. It's the ability to perform functions that might affect the integrity of the system as a whole. That is the ability to change the key in which you're operating, or the key of storage, or to update system storage that maybe you shouldn't, that belongs to the system. There are cases where one needs to do that, but you need to be authorized to do so. Similarly with overriding RACF protection, if I want to be able to access, for example, I'm a backup utility, I'm FDR, I'm HSM, and I want to be able to back up or archive data from an entire volume. Well, I need access to that entire volume. I need to bypass what would otherwise be the ordinary system RACF controls. So who needs the authorization? Well, IBM, of course, the operating system itself needs to be able to perform its functions. So ZOS, the base control program, BCP, has to be able to be authorized. And pretty much all of its components, SMS, the storage management system, JES, the workload manager, certainly the IO subsystem, all of those are performing functions on behalf of user programs. And so they need to be able to manage the storage that's available to user programs and manage all of the other resources that are available to user programs. And to do that, they have to have more authority than Joe ordinary user. The same thing is true of middleware, DB2, IMS, CICS. Those are executing, those applications are running usually on behalf of many users, and so they need to be able to do things on behalf of many users. And the same thing with ISV programs such as CA1, the tape management systems, the FDRs, and our products, ACC and SRS, which go and do things like disk space error prevention and allocation standards enforcement, all of that. If we're going to enforce an allocation standard that says a data set must have this naming convention and must have this associated log file and so on, we need to be able to do that in a heightened state of authority. So what doesn't need authorization is the ordinary application program. In most cases, they're taking data in, they're processing it in some way, and they're putting data out. So an ordinary application program or a standard system utility that's doing a copy or doing a sort, that's doing the typical read, process, update, write function, doesn't really need authorization. It's dealing with its own data. And it's only the really system functions that need authorization. So
hey, Steve.
Authorized, yeah.
Can you pause here just a second? I've had multiple people report that they're unable to see the slides. It sounds like if you refresh your browser, if you're not seeing the slides right now, go ahead and just hit refresh. We'll pause here for just a second while you do that.
Oh, okay. I don't think I have to do anything here.
No, I had somebody refresh a second ago, and they said that worked for them.
Okay.
So,
all right. So we'll give everybody a second. The slide you should be looking at now says, what is authorization?
Yeah, I can see it on my end, but I think that's because I'm logged into the management side of things.
Yeah.
So, okay. I've
Um,
had a couple other people say that they're seeing slides now, so let's go
all right.
ahead and
So
continue.
I see a thumbs up, so we'll move on. Okay. Um, so when we talk about authorized code, and this is the fun part of working at a vendor or working at an ISV, you get the right stuff that's authorized code. IBM defines authorized code very simply. It's code that's either APF authorized, and we'll talk about the authorized program facility, the APF mechanism in just a bit, or that operates with a PSW, where the PSW is running in key zero, or the PSW is running in supervisor state as opposed to problem state. If any of those three things is true, then the program is running authorized, and it can switch between those authorization types. An APF authorized program can switch into key zero, it can switch into supervisor state, it can switch back to problem state. And so the line between authorized and unauthorized is really these three things. And so this is the point at which integrity becomes important. Authorized code can do anything it wants. It's essentially as mentioned in the ZOS basic skills. And if you're new to ZOS, the ZOS basic skills IBM website is really a good one to look at. And this talks about the system integrity statement. It's essentially an authorized program. Essentially, it is an extension of the operating system. Just as our ACC and SRS product, we have to intercept, for example, SRS. If we're going to prevent an out-of-space error, we have to intercept the end of volume call and dynamically add a volume to the data set. Well, that involves updating a whole bunch of system control blocks, the JFCB, the TIOP, the DSAB, the SIOT. And all of that, obviously, if you don't do it correctly, well, the saying is, as I say here, programs running authorized code are only a single instruction away from an unscheduled IPL, because you can do pretty much anything you want. You can switch to supervisor state. You can modify those system control blocks. Hopefully, you're doing it for some reason, like you're going to extend the data set to new volume, as we do with SRS. But you can do it if you need to bypass security. You can take the ACEE and turn on the special and the operator bits. And again, if you're a system program, if you're a backup program or some sort of data transmission utility, you may need to do that. But it does require understanding what you're doing in authorized code. And so programs in general need a way to invoke authorized system functions. Even an ordinary program is going to need to do reading and writing. Of course, reading and writing involves going out to the disks and pulling data off the disk and bringing it into storage. And so every program needs a way to invoke a potentially authorized system function, which is usually done via an SVC or a PC instruction. I might do a get main or a get or a put. What happens once I issue an SVC, if I issue a catalog locate, for example, an SVC 26, to say, given a data set name, tell me what volume it resides on, well, the system can do that in an authorized manner because it's doing it as part of the SVC. Your program that's invoking catalog locate doesn't need authorization to do that. And so the way a program invokes an authorized function that it needs is usually via a macro, system macro, catalog locate, get main, free main, all of the IO macros and so on, which result in SVC or PC program call instructions that will themselves be part of the operating system and operate authorized. Or you could invoke an APF authorized program. It's possible for an unauthorized program to invoke an authorized one, that's assuming that certain requirements are met. You could invoke a program in the program that is mentioned or listed in the program properties table, the PPT, which is a member of SysOne, or part of a member of SysOne.ParmLab, for programs that need certain special functions, like they can't be canceled or they have to run in T0, something like that. One can also get control and authorized code if you're writing a ZOS system exit or an IO appendage, then those generally run APF authorized. If you're writing a system exit, for example, one of the reasons people don't write system exits often is because they require authorized code, and this is in fact one of the functions within our allocation control center set of products is we can replace the exit routine with a set of policy rules so that you don't need to write APF authorized code. If you want to look at whether a program is APF authorized, I have a little screenshot here of our load library, and this is just a 3.4, 3.2, 3.1 ISPF screenshot, and we'll show you, of course, the program name and the if it's an alias and the size of the program, and then the AC or authorized, the authorization bit, the AC bit in the load library is only on for some programs. It's on here for SRS info. It's on here for another one for UTA $1,000. We don't need to, although most of the DTS code runs authorized, we don't turn on the AC bit, the linkage editor indicator, because you only need those in programs that are going to run as a job step task, and we'll talk about that. So let's talk about APF. So all of this library we just looked at, this is an APF authorized library, dts.r71.loadlib, but not all of the programs in it are marked as being authorized. So let's talk about the authorized program facility. This is one of the three ways that we can run in a privileged state. We can either be APF authorized, we can be supervisor state, or we can be key zero. APF is the most common way to do that, and the authorized program facility is that set of ZOS functions or ZOS functions and features that identify programs that are APF authorized, identify programs that can perform system functions. APF also prevents you from using macros and SVCs or prevents you from using certain macros and SVCs unless you are APF authorized. So APF identifies those programs that need to do things that can perform system functions. It restricts the use of those system functions to particular macros and SVCs. Certain ones of them can only be called by APF authorized programs. And probably the most important thing it does is it fetches all of the modules in an authorized job step task only from authorized libraries. So how does a program get APF authorized? A program is APF authorized and therefore able to do, as we said, anything it wants. If it resides in the linked list concatenation, there's a couple of exceptions, but if it resides in the linked list concatenation, if it resides in LPA, or it resides in the APF list, that is the system list of libraries that are APF authorized. And the first program in the job step is linked with AC1. That is, when you link the program, you specified AC1 in the linkage editor control statements, or I should say binder control statements nowadays. The first program, the job step program, has to be linked AC1, and as long as all of the subsequent programs that first program calls come from APF authorized libraries, not necessarily the same one, but other APF authorized libraries, then the job step is authorized. And so AC = 1 has no meaning for any program that is not in an APF authorized library. It also really, one should not link all programs that are going to reside in an APF authorized library as AC = 1, because if, for example, I had some of these programs, they are linked as AC = 0, meaning they are going to be called from a job step program. If I had linked them AC1, if I had linked SRS stow here, AC1, that means if I called it independently, it would be APF authorized because it's coming from an authorized library if it was linked AC1. I don't want it to be callable authorized independently, and so I link it as AC0. So the system decides if the program meets all these requirements as it's running or as it's initiated, as the job step task starts the program. It says, does the first program reside in the linked list, concatenation, or LPA, or in the APF list? And is that first program linked AC1? If it does, it turns on a bit in a control block called the job step control block, the JSCB. It turns on the JSCB off bit, and any subsequent execution, any subsequent load from a non-APF library will get you a System 306 admin. Hopefully everything else will come from APF authorized libraries, which means the entire job step continues to be authorized. So we mentioned it was the link, to be APF authorized, you got to be in the linked list, you got to be in LPA, or you got to be in the APF list. The APF list is that list of libraries that the system programmer has decided should be APF authorized. And so this is a critical resource. It's usually protected by a RACF facility class and dataset class. It consists of sys1 link lib, sys1 SVC lib, and it can be either static or dynamic, although I don't think anyone nowadays probably has a static link list. It's almost always a dynamic link list defined in the prog.exec member of sys1 parm lib. So it's any of these sys1 link lib, sys1 SVC lib, and any libraries that are in the link list concatenation, and any libraries you've added to the APF list, either via prog.exec or via the console command setprog. Setprog is a really powerful console command that will allow you to do things like update the APF list, update what's in LPA, update the linked list. And so we've got a couple of examples here. If I wanted to add a library to the APF list, I'd say setprog APF add, and give it a dataset name and a vol here, or a dataset name and the character string SMS if the library is SMS managed. And presto, anything executing, any job step executing an AC=1 program from that library will be APF authorized. Similarly, if I want to add a library to the linked list concatenation, I can use a series of setprog statements to do that. I can say setprog linked list define and give it a name, and copy the current contents of the linked list into my new name, new linked list name. And then I can say, take that linked list and add a data set name to it. Setprog linked list add, name equals my linked list name, PS name equals the data set I want to add, and then I activate it. So it's possible to dynamically nowadays, didn't used to be possible many years ago to do this, but to dynamically create a new linked list or add or remove things from the linked list concatenation. And if I want to display any of this, there's a display prog command, display prog APF linked list or LPA that will allow me to display what's in the APF list right now. And just a reminder that if I'm displaying what's in the APF list, well, if I'm running with a step lib and it happens to be all APF authorized libraries, then yes, the job step will be APF authorized. But if there's any non-APF library in that concatenation, I don't get an error, but the job runs as non-APF authorized. It runs as a Joe Ordinary program. So because the reason for that is if I allowed non-APF libraries in the step lib concatenation along with APF libraries, and and the entire thing was APF authorized, anyone could counterfeit a module into my non-APF library, and then I'd have my program executing APF authorized. Okay, so all of this, the APF authorization, the APF facilities in support of ZOS system integrity, of that system integrity statement. And the way that ZOS supports this system integrity is with an authorization mechanism like APF to segregate system functions from user functions. System functions like operating, system functions like backup, restore, all kinds of things like that. The way that ZOS does this is these authorization mechanisms are there. The APF authorization mechanism, plus just the way ZOS works, of course, there's a virtual storage. There's a private address space for each user, so even an ordinary user cannot destroy the storage by another user. They can't destroy common storage because there are storage protection keys associated with all of the virtual storage pages. And if you are writing to a virtual storage page, or reading from it, but if you're writing to a virtual storage page, and it's one that perhaps belongs to common storage and not to specifically your storage, you won't be able to do so because it's protected by a storage protection key. There's also a separate storage protection for low storage for the first 512 bytes of storage, because that's where a lot of system I/O interrupt information is kept. So even an authorized program will have trouble updating low storage. And LPA, LPA is there's a page protection facility for LPA where even an authorized program cannot directly update LPA. So we have a bunch of different mechanisms for how ZOS supports integrity. We have APF, and the second one of the three ways to get authorized is to operate in supervisor state. And so we have a picture here. I didn't really label it, but we have a picture here of a PSW, a program status word. And the PSW, of course, tells us what the next sequential instruction is going to be. It's a 128-bit sort of special purpose register. And the second half, it tells us what the next instruction to be executed is going to be. But the first half of it, the first 8 bytes of it, are control information. Am I in problem state? Am I in supervisor state? A whole bunch of other control bits are there in the first 64 bytes of the PSW. Bit 15 is one bit that says I'm either in problem state if it's off, or I'm in supervisor state if it's on. And these are very much method one of getting authorized, or getting heightened privilege, is APF authorization. Method two is to operate in supervisor state. In problem state, which is the normal execution mode of the PSW for an application program, you can't execute any instructions that are going to change the PSW. Of course, every instruction implicitly changes the PSW by advancing to the next sequential instruction, but you can't change the PSW storage key. You can't change the PSW problem state bit. You can't change bits that are controlled by the control registers and so on. So a problem state program usually operates in key 8, which is the default user key, and therefore it cannot bypass RACF, and it can't switch into supervisor state unless you're APF authorized. Whereas in supervisor state, which is the normal mode of execution for a system routine, so if I'm writing an SVC, if I'm writing a routine that's going to do something where I modify system control blocks, I'm DB2, I'm IMS, I'm ACC or SRS, I will usually operate in system, excuse me, in the supervisor state, which means I can execute any valid instruction. Problem state programs cannot execute certain types of instructions, primarily those that change the PSW. Supervisor state programs can do anything they want. Usually, supervisor state program will operate in key 0. It doesn't have to, but it will operate usually in key 0, and thus it can bypass system security. It can turn on flags that allow RACF to be bypassed. I can set bits in the ACEE or in the JFCB or the JSCB that will allow me to cause system security to be ignored. Okay. So within ZOS, there are really 2 types of instructions. There's unprivileged instructions, and all of this is in actually a rather thick manual called the Principles of Operations Manual. It tells you everything you could possibly ever want to know about a ZOS system. But it's really rather dense. Unprivileged instructions are those ordinary instructions that don't modify the PSW, so they operate in problem state. They operate on data and storage. They operate on virtual storage pages, add, subtract, load, move characters, or they operate on registers, add 2 registers together, or 2 registers, all kinds of things like that. So and the unprivileged instructions can be executed in problem state or in supervisor state, because they do sort of ordinary things. And they're sort of the unprivileged instructions can be classified as sort of general instructions, move characters, load address, add registers, decimal instructions that operate on decimal format data, add packed, zero and add packed, subtract packed, all the packed instructions, floating point instructions, a few others that any program can execute. Opposed to that are the control instructions, which are actually sort of divided into three categories. You usually think of unprivileged instructions and privileged instructions, which is a major differentiation. A privileged instruction can only be executed while you're in supervisor state. That is, while the supervisor state bit 15 of the PSW is on. So it's a privileged instruction. If I try and execute a privileged instruction in problem state, I get a 0 Charlie 2 add-in, which is a privileged instruction exception. And they can operate on any data on Earth. They can change the PSW, they can change the storage protection keys, they can change the supervisor state. So privileged instructions are ones that are used by system programs, by vendor programs, by middleware programs that do things for groups of users. There's a set of I/O instructions for the channel subsystem. These are primarily the reads and writes that go to the I/O subsystem. And then there's a third class of control instructions that are, and there are, I believe, 27 of them. And these are the semi-privileged instructions, which provide some sort of system-level function, but can be executed in problem state. Usually, they may be subject to some other additional authority tests. You could be APF authorized and running in problem state, and that might be what's necessary to execute a semi-privileged instruction. These might be things like program calls, PC calls that are done as part of system macros, things that are done perhaps as part of the L-space macro or things like that. So they can be executed in problem state. They might or might not require APF authorization. They might or might not require some special key. And if you don't execute them correctly, if you don't meet these additional authority tests, then you get either a system 0 Charlie 2 or 0 Charlie 6, which is a specification exception, or some other add-in that will say you tried to use the semi-privileged instruction, but you weren't in the proper state to do so. And probably you were in problem state, but you weren't APF authorized. So we've talked about APF authorization. We've talked about problem state versus supervisor state. The thing that really protects the system as a whole is storage protection. And here we talk primarily about virtual storage because that's what we use in ZOS. It is possible to use real storage, but we generally in ZOS talk about virtual storage. And storage protection allows us to ensure that only programs that have the proper storage protection, that are operating in the proper PSW key, can change data in any given virtual storage location. So there's really two types of storage protection. There's store protect, which prevents you from putting data into storage or from overlaying data in storage, and fetch protection, which prevents you from retrieving data from a storage location. And then there's two other types of storage protection. There's low storage protection, which we sort of mentioned, prevents the update of the low storage system areas, basically the first couple of pages of the operating system, location 0. And then something that's relatively new, it's about 10 years old, but 15 years old, but instruction execution protection prevents you from executing instructions in a particular storage location. So I can get a piece of virtual storage, I can fill it with instructions, but if that particular storage location is subject to instruction execution protection, the system won't execute the instructions that are in that location. And all of this to prevent the updating of system control blocks or buffers or any other virtual storage location where you might hurt something if you overlay it, or you might get access to something that you're not supposed to get access to if you try and read from it, if you try and fetch it. So let's talk about storage keys. I really should have probably another legend on this, but this is not a PSW. This is a page in virtual storage. Every page of virtual storage has a storage protection key associated with it. In fact, it has a bunch of bits associated with it, six or seven bits. The most important which are the first 4 bits, the access control bits. That is, it's the storage key for this page. And because it's 4 bits, I can have 16 different storage keys, so values 0 to 15. They're referred to as the access control bits, but people generally call them the storage key of the page. And that controls, each page has a storage key associated with it, which is not known to ZOS, is not part of addressable storage. But each page has a storage key associated with it that controls whether or not you can access this page. There's a fetch protect bit that says whether or not you can access it for read or write. And then there's some other bits that say this page was recently referenced, this page was recently changed. I've got a little error here. It says matched against PSW key mask. This is actually matched. The access control bits are matched against the key that's in the PSW, not the PSW key mask, which is something a little different. And we'll correct this in the version we send out. But the access control bits are matched against the PSW key when I access the page. So if the page is in key 5, and I'm trying to access it with a PSW key of 6, I may or may not be able to access it depending whether I'm trying to do a fetch or a store. The fetch protect bit, which is a separate bit from the access control bits, controls whether or not, it says here it controls access for write. That should say control access for read. It controls access to whether I can fetch from that page. So normally it's off. And any key, it doesn't matter what key my PSW is in, if I'm operating in key 5 or 6 or 7 or 9 or 11, as long as that fetch protect bit is off, I can access and read from that page. But if that fetch protect bit is on, then in order to read from that page, I must also have a PSW key that matches the key of the page, the access bits. Okay, so how do I know what key I'm going to get for my storage, for my virtual storage? Well, it's determined by the subpool in which the storage resides. ZOS, when one goes to get virtual storage, whether you're the operating system or whether you're a Joe Ordinary program, you get storage in a particular subpool. And a subpool is just a collection of attributes that define a type of storage. So I have subpools that are defined by location. Is this private storage? Is this common storage? Is this LSQA? I have storage pools that are fetch protected. I have storage pools that are fixed and can't be paged out or are pageable. I have storage pools that are owned by, storage subpools that are owned by the task, the TCB, or maybe the job step, or I have system storage that's owned by the system as a whole. And so depending upon what subpool I specify when I go to get my virtual storage, which is done by get main, free main, storage obtain, storage release, IARV 64, when I go to get my storage, whether I'm a system program or an ordinary program, I will specify what type of storage I want. What's its location? Should it be fetch protected? Who's the owner? That is, what subpool would I like? And so certain types of subpools always get the same key. Their fixed storage key is always assigned. They always get the key of the user. They always get key 5, key 8, whatever it is. More commonly, the storage key is based upon the key that, the protection key that is in the TCB or the SRB under which the task is operating. Or in a lot of cases, the caller of the get main or free main or storage obtain or release macro will select the storage key. I can specify a key parameter and say, give me this much storage, and I want it in key 5. And so together, the type of storage, whether it's an LSQA or who owns it, and any key parameter that you specify on the macro will determine what the keys are that are associated with that piece of storage. So the access control bits that are associated with that piece of storage. Okay, and so now I've got a piece of storage with a storage key associated with it. How do I touch that storage? How do I store into it? How do I retrieve from it? That is under control, again, of the PSW. So the PSW could be operating in supervisor state, it could be operating in problem state, but it's also going to be operating with a PSW key. And that PSW key is, like the storage key associated with the storage, is 4 bits. So I can have keys, keys 0 to 15, 16 possible keys. And it's bits 8 to 11 of the PSW. And so programs, I say here programs executing with, and we'll correct this, I've said PSW key mask, and it's a little confusing. Sometimes people refer to the PSW key mask, and what they're really referring to is the PSW key. There is a separate a separate field in the PSW called the PSW key mask, which says which keys you're allowed to use. The PSW key is which keys are you using. So programs executing in key 0 are, in Linux terms, super users. It's the master key. They can access or read or write any storage that they want. Keys 1 through 7 are system keys. And so this is a heightened privilege key. And it's generally your system control blocks and system routines operate in keys 1 to 7 or in key 0. So if I need to access a piece of storage that's in key 5, as is often done by ZOS allocation, I don't know, if I just need to access it, I don't have to be in key 5. I can be in any key as long as it's not fetch protected. But if I need to write to it, if I need to store into that piece of key 5 storage, then I must be operating in key 5. Keys 8 to 15 are user keys, and almost everything operates in key 8. If you're an ordinary ZOS program, an ordinary user program, you're going to be operating in key 8. So the programs executing with keys from 1 to 15, that is anything but key 0, can store or they can fetch any piece of storage as long as it's got a matching key. They can fetch from any piece of storage unless it's fetch protected, in which case they have to have a matching key. And then there's also key 9 storage, which most programs you can operate in either key 8 or key 9. It took a while to figure out who uses key 9. It's mostly seems to be used by CICS. If you look into the Principles of Operations Guide, there's some talk about something called storage protection override control. Key 9 storage, as it turns out, is accessible read-write by any program if this CVT bit is on, and it's basically always on. It's mostly used by CICS. So generally speaking, an unauthorized program is going to operate in key 8, possibly key 9. And whether it can reach out and touch that storage and read from it depends on whether it's fetch protected. Whether it can store into that particular piece of storage, it can, but only if the PSW key matches the storage key associated with that page. Okay, so this is basically this slide is basically saying the same thing. The PSW key gets assigned when the step's initiated, or when the particular task is dispatched. There is a PSW key mask in Control Register 3 that initially gets set to the PSW key, and it says these are the keys that the user can switch to. And for a non-APF authorized program, it's key 8. There's only key 8. So an unauthorized program can't change the PSW key, although the PSW key as it's operating might change when you invoke an SVC, or when you invoke a program call to do something. When the program calls out of its own storage or calls out of its own execution path, the key may change, but when the function that it calls returns, hopefully it will return in the same key. Authorized programs, which are key 7 or key 0, supervisor state or APF authorization, can change any key. So in general, if your PSW key is 0, you can do anything you want. It doesn't matter whether it's fetch protected. You can store or fetch into anything. If your PSW key is non-zero and it matches the storage key, this key of that storage page, then you're allowed to store into it. And if it's not fetch protected, then you're allowed to store into it. If you're operating in some non-zero key and the storage key doesn't match the PSW key, the key of the storage page doesn't match the PSW key, well, then you can't store in it. You'll get an OC4. If you're trying to fetch from that page and it's not fetch protected, however, you can read it. You can read any page as long as it's not fetch protected, no matter what key you're running. But if it is fetch protected, then you're going to get, again, an OC4 unless your PSW key matches the storage page key. Okay, so how do I go about switching keys? Well, we said it could occur as a result of an SVC or a program call, because a problem program state really can't, a problem state program really can't switch keys. But if you are an authorized program, an APF authorized program, you can switch keys. You can switch keys, and you can switch your state from problem state to supervisor state and vice versa. Generally, that's done, the switch from state, problem state to supervisor state, or key 0 to some other key, or some other key to key 0 is done with a macro, mode set macro. But ultimately, an authorized program can go and issue a whole bunch of key-related instructions. And these are either semi-privileged or more likely privileged instructions that can only be executed if you're operating in supervisor state. Insert PSW key, set PSW key, move characters with key, move characters to secondary, move characters to primary. There's a whole series of instructions. There's something like 2,000 ZOS instructions now. And so there's quite a few that are related to the protect key. And so who uses what keys? Well, one can use pretty much any key one wants, but there's some sort of conventions for which execution keys and therefore storage keys systems tend to use. Key 0, of course, is the king of the hill. Anyone that using key 0 can alter any storage they want, except for LPA pages that are page protected. But anyone can alter any storage they want mostly. And so key 0 tends to be used by the base control program, by ZOS functions, by ISV products that need to do something to alter a system control block. JES and TSO tend to run in key 1. ISVs tend to run in key 2 or key 4, although there's no requirement. They can run in pretty much anything they want. Key 3 is something called the availability manager. There are a few other things that will also run in key 3 in ZOS. Key 5 is the one that we tend to work in most with VTS because it's the data management key. DFSMS, DFP, allocation, and the volume is all in key 5, and that's where our code tends to run. VTAM is key 6. Also, some certain amount of allocation code also runs in key 6, and so ACC and SRS run in key 6. One of the other reasons that you want to use a system key and you want to use storage protection, a non-zero key, is to keep a program, is to make sure that your program is not accessing storage it shouldn't, and if it does, you'll get an OC4. So generally, system programs operate in system key, 0 to 7, and user programs in a user key, which is key 8 or maybe key 9. There are a couple of other types of storage protection we mentioned. Low address protection, basically the first 512 bytes of the first 2 pages of storage, virtual storage, one cannot store into. There's what we mentioned, instruction execution protection, or IEP, prevents programs from being executed if they reside in a particular block of storage. It's actually a bit set that's associated with that particular page frame, very similar to the access control bits, but it's actually a bit that's set in the page table entry or the segment table entry. And when you do a storage obtain for a particular subpool, and this really protects only private subpools, but when you do a storage obtain, if you specify executable equal yes, which is the default, well, then you can put instructions into that virtual storage location and they'll be executed. But if that virtual storage location really should contain only data, then you probably want to get it with executable equal no, so that in no event can someone stick instructions into your buffer or whatever it might be, and try and execute them from there. And then we mentioned that certain pages, LPA and nucleus modules, have a separate page protection bit on each page where nobody can store into them because nobody should ever store into them. Okay, the last topic is the program properties table. The PPT is for programs that require special attributes. You can modify it with the set command to say I want to use this program properties table. The set is actually contained in member sched XX of sys1 Parm Lab. And there's one statement for each program, and each program can have any one of a number of attributes. So you can say programs of this name, I want them to be uncancelable, or I want them always to run in this protection key. I always want them to run, in key 5 or key 7 or key 9, whatever it might be. I want them to be non-swappable. I want them to be able to bypass rack-out. Usually, of course, then the program properties table is for things like components that are part of the operating system that are middleware like IMS or OAM, or perhaps parts of the tape management system might reside in the program properties table. If you've got certain programs I want to ignore the IF-USI region limits, I can set that, and it doesn't matter what the IF-USI exit does, it can be overridden. All in service of system integrity. So all of this is what makes ZOS probably the safest system to run on anywhere in terms of its integrity. So how do we ensure that? Well, the real way to ensure it is programming practices. If you have occasion to write system code, you generally want to avoid key 0 unless you really need it. Certainly, you want to avoid things like, that used to be quite common, although the auditors never allow it anymore if they discover it, the magic SVC that will, when you invoke the SVC, will return control in an authorized state. In terms of other programming practices for integrity, particularly if you're a server type program and the caller gives you some piece of storage, you want to access that in the caller's key and not in key 0 or something like that. You want to validate any control blocks via the chain of control blocks and not just via an eye catcher, so that no one's counterfeiting eye catchers for you. There are 2 health checks that are sort of common system integrity. If you look for health checks, there's one called RACF sensitive resources and another called CSV APF exists to make sure that your APF authorized libraries are protected. A bunch of RACF profiles, of course, protect various commands. There is a security portal, which you have to register for IBM Z and Linux One to tell you about the most recent vulnerabilities that IBM has discovered. And so that might be worth a look. Or you might, again, in terms of programming practices to ensure system integrity, you can run things like ZAX, the Authorized Code Scanner, or ZACM. These are 2 products from IBM that basically will scan your authorized code and look for vulnerabilities in authorized code, particularly your SVCs. And where is all this documented? Things to look at are the ZOS basic skills. There's a section on integrity. The principles of operation tells you all about protection keys, PSW key masks, and so on. There's actually some good sections in the extended addressability guide about storage protection, and in chapter 21 of the authorized assembler services guide. Next month, we will talk about generation data sets. We're continuing on with our webinar series where we're trying to sort of introduce topics that maybe aren't terribly widely known or widely known within GOS, but not within the wider world. We're trying to introduce those, particularly to people that are new to the platform, but and also at the same time try and throw in a few tricks for people that are somewhat older dogs. And so we're going to talk about generation data sets, which are really unique to IBM. They're unique to GOS, and they're particularly useful, but they do take a little bit of work to understand them. And so at this point, I will turn it back over to Ray for any questions. And I know we're running right up against the hour, but we still have a few minutes left if there are any questions that might come up.
Well, at the moment, we don't have any outstanding questions. So if you do have any questions, feel free to drop those in the chat at this moment. But if something comes to you later, feel free to reach out to us, support@dtssoftware.com. We're still taking emails there for support questions. We will be migrating our support processes over to Precisely here in the next week or two, but you know, for now, we're still using the same old email address.
Thanks, Ray. Also, if you're looking for our manuals or looking for product downloads and things like that, that is now available on the Precisely website. It's now we're now going under the SyncSort storage management umbrella, and so they're the same products, but they have been rebranded as SyncSort Space Recovery System and Allocation Control Center. And we're always interested in your suggestions for anything that you think would be useful in the products, anything problems that you might have that we might be able to help attack and address. We're always interested in those. And thanks everybody for attending, and we'll see you again next month.